Good morning, good morning, good afternoon. Hope all is well. Hope everyone's doing all right. I think a few people trying to still get the audio straight, so I'll give them 1 second and then we'll go ahead and get started. All right, no problem at all. All right, good afternoon, everyone. Hope all is well. Hope everyone's doing all right. So, last class, we closed out chapter 4. So today we'll get into chapter 5. Um, do 5-1 or 5-2, maybe 5-2 as well, just see how short 5-1 is. I would love to have given you a break, but you got a break Monday. We're out of class on Monday, Juneteenth celebration, so no class on Monday. So I won't see you guys until Wednesday. So that's why we have to do at least one section, maybe two, out of chapter 5. Before we close out the day, should we plan to review and take tests? It's up to you. I would say yes. You want to get out of if you're ready to get out of chapter 3 and 4, then most definitely go ahead and take it out. Take it. Remember, it's going to be at your own time because I'm going to post in the math lab soon. I should have did. I meant to do it I meant to do it Monday, so I'm going to do it. Before the day is out, I'll post that second test. But yeah, most definitely, if you're ready to knock out test 2, then most definitely go ahead and do that. So because you see me getting into chapter 5, and so the quicker you can get out of chapter 4, the better. But it will be, at your, whenever you have the free time to do it, we will not be doing it in the class. All right. Any other questions about that before we close? Not close, before we go to chapter 5. Everybody good? Everybody straight? Okay, so chapter 5 takes us into probability. Like I said, depending on how long 5.1 is, that'll dictate whether we get into 5.2 or not. But we're looking at randomness first. So people are not good at identifying truly random samples or random experiments. So we need to rely on outside mechanisms such as coin flips or random number tables in order to actually get randomness. All right, scrolling up some. Okay, so random means that no predictable pattern occurs and that no digit is more likely to appear than any other. All right, everybody done with black? Probability is used to measure how often random events occur. An example of that, there is a 50% chance that a coin will land on tails. Next, everybody done with the red? All right. So theoretical probabilities are long run relative frequencies. It is the relative frequency at which an event happens after infinitely many repetitions. All right, are we up to the green statement? Anybody holding on to the black sentence? All right. So, for example, when we say a coin has a 50% chance of coming up tails, we mean that if it were possible to flip a coin infinitely many times, then exactly 50% of the flips would be tails. All right, scrolling up some. All right, so empirical probabilities are short run relative frequencies based on an experiment. All right, so empirically, if you toss a coin 10 times and get 7 tails, your empirical probability is getting tails is 7 out of 10, which is 70% chance. So when we talk about theoretical tails, it would be 50%, but empirical probabilities are based on short run relative frequency. So if you only get 10 times and you get 7 out of 10, that's 70% chance of landing tails. So empirical probability tells us how often an event occurred in an actual set of experiments. All right. And then theoretical probability are based on theory and tells us how many times an event would occur if an experiment were repeated infinitely amount of times, infinitely many times. All right. Simulations are experiments used to produce empirical probabilities. I look on blue, I scroll up on blue. All right. So investigators use them with the hope that their experiments simulate the situation they are examining. You see not much calculation in this section, just a lot of introduction. So, example of that, one could use a computer program to simulate flipping a coin 100 times. All right, theoretical probability measure the proportion of times events would occur if an experiment is repeated infinitely many times. Right there. So this means it is impossible to carry out this task. We can use empirical probability to estimate and test the theoretical probability. Rolling up. So that's all 5.1 was, just setting the platform, setting the foundation for probability. We can go ahead and knock out 5.2, but any questions or anything out of 5.1, anything that was said? Anybody? All right, so we get into a little calculation with 5.2. Feel okay with me scrolling up? So 5.2, finding the theoretical probabilities. First, start off with defining what an experiment is as any process with uncertain results that can be repeated. So much as are you putting this recording things? Yes, I'll be posting it. I'll try to get that post to you tonight, if not most definitely by tomorrow. So yeah, I will be sending this out to you guys. I'll send it to the email and it will be in your Canvas announcements. So an example of an experiment is flipping a coin. Sample space, all possible outcomes of an experiment. So when you talk about flipping a coin, the sample space of flipping a coin, the heads and tails, so those are all of your possible outcomes of flipping a coin. All right. And then an event, it would be any collection of outcomes in the sample space. So if I want to know the probability of landing tails, tails would be my event. All right, so then we do the complement. Complement is going to be all outcomes in the sample space that's not the event or that are not the event. So if my probability, if I'm looking for the probability of landing tails, tails is my event, then the complement of my event, when you talk about flipping the coin, would be heads. So everything that's not tails. In this case, it's on tails and heads and tails. So heads will be the complement of tails. Everybody holding on to events. All right. So notation, if E represents your event, then the complement of E is E with that superscript C. So E with a small c up to the right. That represents the complement of your event. So if your event is A, then the complement of your event is A to that C superscript. Mhm. So the summary of probability rules, we have 1 and 2 here. Got a few more as we progress throughout the chapter. All right, so first rule is that your probabilities will always be in between 0 and 1 inclusive. So that means it is possible to be 0% or 0, and it is possible to be 1 or 100%, but they have to be in between. You cannot be greater than 1, cannot be less than 0. All right. Second rule, all three of these are the same rule, just manipulated in a certain way, depending on what you have and what you're trying to find out. So if you're looking at the probability of A, your event, and you wanted to know it, but you knew the complement, if you subtract your complement from 1, then you can find the probability of your event. Or if you knew the probability of your event, but you want to know the probability of the complement, subtract that from 1, that will be the probability of the complement. Or in other words, the probability of your event plus the probability of the complement of your event will be equal to 1. Once again, all of these are the same formula, just manipulated according to what you have, what you're trying to find out.
Does, when you're using parentheses there, is that meaning probability of, not actually multiplied by?
Exactly. Exactly. You're in statistics now, so statistics got its own set of rules and language. So right, you're absolutely correct. So this is not multiplication, it's the probability of A.
Okay, thanks.
Good question, good question. We got 2 or 3 here. Let me know if I scroll up too far. Oh, it's just notation. Somebody asked if it's not multiplication, what it's just notation. This is what we're gonna do right here to find the probability of your event. But that, once again, that's not P times A, that's the probability of a event A. And I must have wrote it in my other notes. I thought I wrote that somewhere here. Must have wrote it in my other notes. Yeah, so sorry for not writing that here. But this is how we calculate the probability of A. Yep, no problem. So to calculate the probability of A, or the probability of your event, you would take the number of outcomes in your event, place it over the number of outcomes in your sample space. All right. So let's look at this first example. We're still talking about the probability of landing tails. So our sample space is heads and tails. There are no other options there. So the number of, just like P of A is the probability of, let me say event A. That's the probability of event A. N, that's in parentheses S. That's the, I want to go another color since I got green right there. Let me do it like this. This. So that's the notation there. Number of outcomes in event A is in parentheses A. Number of outcomes in your sample space in parentheses S. All right, so going back to purple, we have heads and tails. As far as your coin is concerned, that's the number of those are outcomes when you flip a coin. So the number of outcomes 2. We talk about tails is your event. It's only one outcome there, which is tails. So the number of outcomes in your event is just 1. So the probability of landing tails is going to be 1/2, which most of us already knew that it's 50% chance. So 1/2.5, which is 50%. But that's the thought process behind calculating your probability, and that's the foundation of what you're going to be moving forward, trying to calculate your probability. You need to know the number of outcomes in your sample space, number of outcomes in your event, basically event over sample space, and that'll be your probability. Okay, scrolling up. All right. So first real example, 10 dice in a bowl. So we reach into a bowl that contains 5 red dice, 3 green dice, and 2 white dice. What's the probability of picking? You just write that down for everybody don't read. So what's the probability of A getting a red die, B getting a green die, C getting a white die? All right, so let's look at A, probability of getting a red die. So first we need to know the number of die that are in the bowl. See if we reach the bowl, right? Reach the bowl, yep. So we add them all together. We got 5, 3, and 2. That's 10 die, 10 dice in the bowl. So that's the number of our sample space. Then if you're talking about a red die, we need to know how many red die we have, or how many red dice we have. Keep flipping those in my room, but we have 5 red dice. So now that you know the number of red dice that you have, you know the number of total dice that we have. So that's 5 over 10, and that'll be 1/2. All right, do the same thing for green. Once again, our sample space is 10. That doesn't change, but there are 3 green dice. That's 3 over 10. And that'll be the probability of getting a green die. And for the last one, a white die. Sample space is still 10. There are 2 white dice. 2 over 10 will reduce down to 1 over 5 as our probability. Any questions? Any questions? All right, so if we roll 2 dice and add the outcomes, what is the probability that the sum of the 2 dice is 7? All right, so let's look at how we're going to establish our sample space first. And whenever we deal with probability, you need to establish a number of the sample space. Even if you don't list them all out, you at least need to know how many options you have in your sample space. So when you're talking about a single die, you play board games, something along those lines. You have 6 faces, and right here in the purple, you have these pips on each side. One pip would be 1, 2 pip would be 2, 3, 3, and so on. So we have 6 faces, and that represents the numbers 1 through 6. So now here, if you're talking about the different combinations that can be created when you're rolling 2 dice, that's when die 1 is 1, die 2 is 1. Die 1 is 1 and die 2 is 2. Die 1 is 1, die 2 is 3, and so on. But then you have to go die 1 being 2, and then 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2, all the way down to 6, and so on. So instead of going through all that, trying to list out all of our numbers, we use the fundamental counting principle, which is over here. It says that if I only picking 1 out of each category, 1 face for the die 1, 1 face for die 2. I count the number of options I have and then multiply them together. So I have 6 options for die 1, 6 options for die 2. Multiply those together. I have 36 as the number of possible outcomes. So that will always work as long as you can only choose one at a time as far as from each category. So if I had a die that had 10 faces and another that had 8, then I would multiply 10 times 8, which would be 80. So that will let you know how many outcomes can be generated. All right, any questions on the number of a sample space? All right, so our event is to roll a 7. So we're talking about all of the different ways you can roll a 7. So that's when die 1 is 1, die 2 is 6, 1 plus 6 is 7. Then we got 2 and 5, 3 and 4. Now when die 1 is 3 and die 2 is 4, then die 1 is 4 and die 2 is 3. Those are 2 different scenarios. So 3 and 4 is 7, 4 and 3 is 7. So then we also have to do 5 and 2 and 6 and 1. So we have 6 possible ways of rolling 2 dice and getting the outcome of 7. Any questions? So we have the number of our sample space. Now we have the number of our event. So then we place the event over sample space 6 over 36, and that reduces down to 1 over 6.
Now, is that something that the problems will tell us, or are we gonna have to figure out on our own, like
What?
how many different ways the die could make a 7?
Oh, that's what they ask when they say right here,
Uh-huh.
the sum of 2 dice is 7. So they would tell you that. They could ask 8. They could have said 8. And so you would just go through and you would do it systematically. Like you wouldn't just be all over the place, do 1 here, 1 plus whatever, and then do 4. Like you would do it systematically. Can I do 1 plus any number to get 8? You know what I mean? Then check 2, then check 3. Just go through your system. Don't just be picking a random, because that's the way to miss it.
Okay. Got
it. Yep. So if you're talking about 8, then there's no such thing as 1 plus, let me see, because we don't have 7. So we'll start off with 2 and 6. And then you would do 3 and 5, 4 and 4, 5 and 3, and then 6 and 2. You see what I mean? But you would do it systematically so you don't miss a combination.
Okay. Thanks.
Yep, no problem. All right, any other questions before we go to the next one? So, let's see, let me get this chart in here. Okay. So we're going to use this chart for the next few examples. It says education and marital status for 665 randomly selected US residents. So here we have an education level. So we have less high school, college or higher in total. Then we have single, married, divorced, widowed, and then total. And we have our numbers. So you get a chance to copy down that chart. All right, scrolling up some. So suppose we select at random from the collection of 665 people. What's the probability the person is married? Chance to write the stuff down, of course, those who are writing. All right, so what is the probability that a person is married? So first, we have to look at our sample space. That's the total number of people altogether. And that total number is 665. And they said that up here as well. 665 people are randomly selected. And then you want to look at the total number of people that are married. And these circles. And married is right here, 408. So this is going to be 408 over 665. Now, MathLab will let you know how they want the answer. If they wanted a decimal percentage or whatever the case may be, I just gave all of them. So MathLab will let you know. Any problems with what we did there? B, what is the probability the person has college education, has a college education or higher? So once again, sample space, 665, college education or higher. That total number is right here, 143. That's 143 over 665. All right. Then see what is the probability that the person is married and has a college education or higher. So we still use 65 as our bottom number. And we talk about married, college education. That's where they meet at. 98. So 98 people are married and has a college education or higher. So we got 98 over 65. Mhm. Any questions? Any questions? All right. Still holding on to red. I'll keep going up. All right, so the word and consists of only those outcomes that are both events. So in other words, what they have in common. The word or consists of all outcomes that are only in A, that are only in B, or that are in both. All right, so next one was the probability that the person is single or married. So I just want to make sure we get a little bit of a Venn diagram on how and or works. So circle A represents, let's say, that event and everything that encompasses that event. Circle B represents the event B. So the shaded part is what they both have in common. If they have something in common, that's what that shade, that's that overlap. That's what that red part represents. And then we talk about or though. Oh, and that also represents and. And is also that shaded, that red shaded part. Now, or would be all of the shaded pieces. So green, red, and purple. So it's all of each circle. So that's the difference between and or. And is just the middle red piece, or is all of AB, even the shaded piece, even the middle red piece. All right. All right, just scrolling up. So we want to find the probability that a person is married or single. So once again, our sample space is 665. So now we go back to the chart and look at married or single. So single people, married people. So according to our chart, you can't be married and single at the same time. I know people have entanglements and all the type of other stuff, but according to the chart, you either married or single. You can't be both. So we took the total number of married people, added to the total number of single people, get 520. And that 520 is our top number over our 665. Any questions? Any questions? So next one, what is the probability the person is married or has a college degree? So we know our sample space is 665. Now there's two different ways we can go about doing it. That's why I says two options here. Um, um, So we got two ways of doing it. So the first way, we can, if you go to the chart, we're talking about being married or having a college degree. Let's go back to the chart. You guys can see it, I think. All right, so marriage is right here, college degree is right here, and of course, we're not going to add the total part. Hold on, let me do this. So we're talking about this and that. So we just add those numbers together. So we're talking about 70, 240, 98, 27, 15, 3. And so that's what I did right here, just add those numbers together. And I got 453. So you add up each individual piece. All right. The other way is you can add up the totals and then subtract what they had in common. So if you were to go back, the total number of married people is 480. Total number of college people hired is 143. And what they had in common was 98. So you don't want that 98. You don't want to count that 98 twice. Because in this 143 is that 98. And in this 408 is that 98. So you don't want to count the 98 twice. Just like when I wrote down the pieces, 98 wasn't written twice. So what you would do is do 408 plus 143 and then minus the 98, and that'll give you 453. So either way, your top number should be 453. All right. Any questions? Any questions? So probability be 453 over 665, which is 68.1%. All right. All right, so mutually exclusive events. These are events that do not have any outcomes in common. They're exclusive, mutually exclusive. It is impossible for these events to happen at the same time. So it goes back to what I was saying about being single and being married. It's impossible to be single and married at the same time. They are considered mutually exclusive. All right. So here's the formula for what we were talking about, what I did earlier with the chart. So this is rule 4, of course. If you want to calculate the probability of A or B occurring, you take the probability of A plus the probability of B, and then you subtract what they have in common. So that was the formula we talked about earlier without introducing the formula. Mutually exclusive events do not have anything in common, so they don't have this piece over here. That's why they just add the probabilities together, because there's nothing in common, which is what we did with the single and married in the other example. Mhm. So we're going to roll a fair six-sided die. Find the probability that the die shows an event. It's an event, an even number or a number greater than two. All right. So look at how we would do this. I'm going to call my event E for my even number and G for greater than two, since I have two different events here. So we're going to find the probabilities of each one of them individually first. So number of our sample space is 6. There are 6 spaces to each die. Talked about that already. Erase these circles. The number of outcomes in my event E is 3 because there are 3 even numbers, 2, 4, and 6. So the probability of getting an even number would be 3 out of 6. Then the numbers that are greater than 2, 3, 4, 5, 6. So that's going to be 4 out of 6. All right. So now you ask yourself, are these events mutually exclusive? No, because they have 4 and 6 in common. So they're mutually exclusive. They would not have any events in common or any outcomes in common. So since they have those 2 in common, we do have to consider those and see the probability of getting an even number and a number greater than 2. All right. Let's scroll up too far, let me know. All right. So even number and a number greater than 2. Once again, our probability, our sample space, the number of our sample space is 6. But if you're talking about being E and G, that's 4 and 6. Those are 2 numbers that fit both categories. So that's 2 numbers that fit that. So 2 over 6 is the probability of getting a number that's even and greater than 2. All right, once you have those 3 pieces, you go ahead and throw them into the formula. Probability of E plus the probability of G minus the probability of E and G plus 3, 6 plus 4, 6 minus 2, 6. And that will be 5 over 6. All right, any questions, any questions? So the next one says find the probability that the die shows an even number or the number 5 on top. And let's scroll up. Sure. So just finished doing the probability of an even number, but you still walk through it. Sample space is 6. There are 3 even numbers, 2, 4, and 6. So 3/6 is the probability of getting an even number. So now if you're talking about rolling a 5, sample space still 6. But how many 5s are there? Just 1. So that'll be 1/6 as our probability of rolling a 5. All right. So are these mutually exclusive? The answer is yes. They don't have anything in common because you have even numbers and then the number 5, which is not an even number. So this means we can just add the probabilities together. All right. So adding them together, probability E plus probability of F, 3, 6 plus 1, 6, give you 4, 6. And you can reduce that down to 2/3. Questions, any questions?
Can you scroll up to the top a little bit for the A5, just like that part?
Is that for the what now? Right here?
Right there, yeah, thank you.
Let me see if I can. While she's finishing up, anybody have any questions or anything? Okay, yep, no problem. So, if you finish copying, then that's fine. I'm not gonna do anything else as far as lecture is concerned. Did 5.1, 5.2. Next class, we'll, see if anybody have any questions and we'll jump into chapter, sections 5.3. Once again, we don't have class Monday. So that's why I most definitely want to get a couple sections in on chapter 5. So I will see you guys on Wednesday for those who are done. Have a great weekend, be safe, and see you on Wednesday. Anybody still copying, scrolling up? That was it right there. Anything else? Anybody else?
Hi, I was a little bit late. Did I miss any announcements in the beginning of the class?
No, I'm just gonna,
No.
I didn't post the second test Monday like I meant to, so I'm gonna do that probably in a few minutes. Well, other than that, nope, just regular class happenings. And whenever I post anything in Math Lab, you still have until August 5th to do it, but you don't want to wait until August 4th to get started, that type of thing. So,
Yes, yes. Thank you so much.
yep, no problem. Anybody else holding on to the notes before I close out? Everybody good? Okay. Anybody need me for anything before I close? Everybody good? All right. Well, you guys have a good one. Be safe. Have a great weekend. And I will see you on Wednesday.